Now let's look at vectors in component form. Before we used to look at a vector in terms of its bearing and its magnitude. Now we're going to look at a vector, for example the vector A, and we're going to look at this vector A in terms of its horizontal and vertical components. So its horizontal components, and think of this in terms of the Cartesian plane, its horizontal components here we call I, and its vertical components we call J. So both of these components make up our vector. And if I was to think about this again in terms of a Cartesian plane, for example, if I had the Cartesian plane and I had a line going from the centre out to the point 2, 3, that means I've gone across 2 units in the horizontal or x-axis, and I've gone up 3 units in the y or vertical axis. So the horizontal component of this vector would be 2, and the vertical component would be 3. So this vector A then could be written as 2i plus 3j. Or it could also be written in matrix form, 2, 3, or another vector form is 2, 3. All these forms are perfectly fine for writing vectors. I prefer the matrix form just for a little bit of ease later on. So 2i plus 3j is that vector. Now this vector has a certain angle here, theta. And if we think about that and our right angle triangles, we're going to use that in a moment. First off, all vectors have a magnitude. If you recall from before, as I said, vectors had a bearing and a magnitude. So we need to determine first what the magnitude of this line would be. It's a right angle triangle. So if I wanted to find the magnitude of this, so the magnitude of vector A, and we use this absolute value notation for the magnitude, or sometimes called the modulus of A, we can use Pythagoras' theorem. And we would say then that that would be equal to the square root of this horizontal component squared plus the vertical component squared. So in this case, that's the square root of 4 plus 9, so the square root of 13. And that is the magnitude of that vector. So just that again, the magnitude is given by the square root of its horizontal component squared and its vertical component squared. If I then wanted to look at my horizontal and vertical components in regards to using some trig ratios to help me, I can actually do that as well. And here I can look at, if I was to call my horizontal component x and my vertical component y, I'd end up with this little triangle, which would have, in my case, the magnitude, which we worked out as the square root of 13, this being x, this being y, and this being the angle theta there as well. And I could come up with 2 trig ratios to help me with this. First off, if I looked at x, theta, and this hypotenuse here of root 13, the trig ratio I would use is that the cosine of theta would be equal to the adjacent side over the hypotenuse, and so therefore x would be equal to the magnitude times the cos of the angle. Likewise, the sine of that angle would be equal to its opposite, which is y, over the magnitude, root 13. So therefore, y is given by the magnitude times the sine of the angle. And this is important because now we can determine what both the horizontal or I component of the vector is and what the vertical or j component of the vector would be through purely the magnitude and the bearing. And that's what we've had before. We've been given the magnitude and the bearing for our vectors. So all vectors we've had up until now, we can now convert and give them a horizontal I component and a vertical j component.